Friday, April 13th, 4 a.m. Mountain Time, 2018. The next grand solar minimum, cosmic rays and earth changes. An introduction. This is an article here at Abrupt Earth Changes written by Satya Dobler on January 14th of 2018. Solar minimum, back to the website, if you click on the SFU tab, that's the solar flux units. This is the chart that graphs solar maximum, which you see up here, drops down to solar minimum in 2007, 2008. 2007 was when a scientist by the name of D'Antoni measured UVC. Do you see why he measured UVC, or what compelled him to measure UVC and at least check for it? We were in a solar minimum, headed towards a solar minimum. This is where we are right now, headed towards and in basically a solar minimum. Same thing going on. So when I said we're going to be okay with regard to this UVC, we need to get the shields cranked back up. We need solar maximum to come back. And it will. But let's read what's going to happen in the meantime, or at least what could, with regard to Earth changes during a grand solar minimum. What to expect in a grand solar minimum? How does an increase in galactic cosmic rays affect the Earth's climate and also tectonic activity? Here is a simplified description of the basic mechanism. What I've done here, guys, I've also got just a loop of many pictures playing in the background so you can have something else to kind of look at too while I read this. It's a good article, well written and well researched. Did a great job. A solar maximum is the period with an 11-year cycle of high solar magnetic field and high sunspot count. Sunspots are highly magnetic and visually dark spots or holes in the photosphere of the sun where solar flares can erupt. A solar minimum is the low activity through the 11-year solar cycle. A grand solar minimum is a period of several successive very low Schwab cycles, usually coinciding with phases of climate disruption and in the long term cooling. An example of Maunder minimum 1645 through 1715 that coincided with the coldest phase of the Little Ice Age. The Little Ice Age, from which we have been emerging since 1850, was the coldest period at least in the last 8,000 years. Possible the entire Holocene. Grand solar minima recur in clusters roughly every 200 to 400 years. 27 grand minima have been identified during the Holocene. Thus, we were in grand solar minimum about 1/6 of total time. The sun emits a magnetic field through the solar wind flow of charged particles that reaches as far as the outer planets. This region of the sun's influence is called the heliosphere. Number 1, solar maximum. During solar maximum, when sunspot count is high, a stronger solar magnetic field and solar wind block more cosmic rays from the solar system and prevents them from entering the Earth's magnetosphere, atmosphere, and lithosphere. You see an example right here. Solar wind, cosmic rays bouncing around the solar system. Figure 1, that's this one you see right here. Solar maximum, strong solar wind, high magnetic field strength. Dark sunspots indicate increased release of solar flares and coronal mass ejections, CMEs. Much of the cosmic ray influx is blocked from entering the heliosphere of the solar system. Also, more of the electromagnetic radiation, such as gamma and X-rays from space, are blocked from entering the solar system. Cosmic rays are highly energetic atomic nuclei or other particles, protons, traveling through space at a high speed approaching that of light. Thus the term says rays is technically misleading since they themselves don't constitute electromagnetic radiation. When cosmic rays enter Earth's atmosphere, they disintegrate in a cascade into subatomic particles, which act as a cloud, condensation nuclei by ionization, and thus instigate low-level cloud formation, cloud seeding. Cosmic rays are accelerated by distant supernova and other violent events in the cosmos. The cosmic rays we are concerned with here in the context of solar cycles, high-energy particles from outside the solar system, are called galactic cosmic rays. But recent studies have shown that many of them originate outside of our Milky Way galaxy and thus are actually intergalactic cosmic rays. The Sun itself emits also cosmic rays, solar cosmic rays, but these are of lower energy density and thus have little effect on Earth. So when a quieter Sun emits less solar cosmic rays, this does not counterbalance the cloud seeding effect of the increased galactic cosmic rays. In addition, in solar maximum, the strong solar magnetic field not only blocks out more cosmic rays, but also more of the electromagnetic radiation from space, such as harmful gamma and X-rays. At any rate, during a said succession of several strong 11-year cycles, a grand solar maximum, we see a more benign and stable climate, less variability in precipitation, wind, and a trend of general warming, as in the Roman warm period, the medieval climate optimum, and the recent modern grand solar maximum between 1940 and 2000. The level of activity was high, exceeding 100 in the peak sunspot number. The term grand solar maximum is not often used. But during these very active times, there is only limited increase in solar output in terms of warmth and light, total solar irradiance for the 11-year cycle. This fluctuates in the range of plus minus 0.1%. Total solar irradiance, TSI, is a measure of the solar power over all wavelengths per unit area incident of the Earth's upper atmosphere. It is measured perpendicular to the incoming sunlight. Let me read that one more time. Total solar irradiance, TSI, is a measure of the solar power of all wavelengths per unit area incident of the Earth's upper atmosphere. It is measured perpendicular to the incoming sunlight. At the bottom of the Maunder minimum, the TSI was 1363. At the height of our apparently ending warming period in 2000, it was 1366. That's an increase of only 0.3% in solar energy emission from the coldest climate of at least, or of the last 8,000 years to presently, to 8,000 years to the very presently different one. So it is not as simple as a more active sun emits more heat and thus warms the planet more than an inactive sun by more total TSI, or total solar irradiance. This simplification often gets construed by the proponents of the theory of anthropogenic climate change, when they argue the variability in solar activity could affect climate only minimally. As far as temperature is concerned, what is crucial is not the energy that leaves the sun, but how much of this energy is blocked by clouds and how much reaches the Earth's surface, and how much is reflected back into space by ice and snow. TSI is a good proxy for climate, but it is part of the effect rather than the main cause. It has been textbook knowledge that saturating the air, 100% relative humidity, is not always enough to form a cloud or droplet. The water vapor molecules need a site to condense on. This site is called a condensation nucleus, and the process referred to as heterogeneous nucleation, cloud condensation nuclei, CCN, and about 1 micron in size. In a groundbreaking study in December of 2017, Professor Svensmark stated it had until wrongly been assumed that small additional Nucleated aerosols would not grow and become cloud condensation nuclei since no mechanism was known to achieve this. The new thing is that there exists an amplification mechanism that is operating on clouds in the atmosphere. Quantifying the impact of solar activity on climate from observations is found to be 5 to 7 times larger than from solar irradiance, and agrees with empirical variations in cosmic rays and clouds. This can therefore also explain why climate over the past 10,000 years correlates with solar activity. What is important is the connection of solar activity, cloud seeding, and in the long run, snow cover, whitening. In the 2,000 years cycles of grand solar minima, grand solar maxima, are the warm but wet seasons of generally benign climate, solar minimum. During a solar minimum, and particularly in a grand solar minimum, more cosmic rays enter the Earth's atmosphere. Here, these high-velocity particles, mostly protons, collide with the atmospheric atoms and dissociate in a cascading mode into smaller subatomic particles. These particles act as cloud nuclei by ionization and propagate low-level cloud formation. Some particles may reach the Earth's surface and even penetrate it. In this way, more cosmic rays accelerate storm formation, erratic rainfall, snowstorms, hail, local flooding, and in the long run, global cooling. We add to this earthquakes, volcanoes, lightning, and other electric events, and an enhanced risk for solar flares that can disrupt our power grid. But somewhat counterintuitively, grand solar minima, the cooler phases, are historically prone to drought, and due to jet stream disturbances, also singular heat waves and wildfires increase. And we're seeing a lot of that right now. If you guys have noticed, these weird snowstorms, these weird weather patterns, jet streams, ocean currents, there's a lot of things changing on the Earth right now. And this could be one of the mechanisms that's creating a lot of these changes. It is primarily the climate instabilities and erratic weather rather than the actual drop in temperature that initially disrupt agriculture and civilization. And that's true. During the Little Ice Age, temperatures across the northern hemisphere arguably declined only by 1.1 degree Fahrenheit relative to the average temperature between 1000 and 2000 CE, according to Encyclopedia Britannica. But frost and snow events and crop failure were devastating. A normal grand solar minimum initially manifests not so much as a mini ice age, but could more appropriately be called bad weather age. Is that what we're seeing now? And something else that could instigate, and this is me talking, something else that could instigate crop failure is UV. If the magnetic shields get too weak, then there's going to be too much UV come in. Whether it's UVC or not, even if it's UVB, the ecosystem likes UVA. So if too much comes in and it's too intense, it's going to be very stressful on the crops. Okay, back to the article. Even when, in a given year, average temperatures are only slightly below normal or even average, all that is needed is one unseasonal late snowfall or hailstorm to ruin crops for that season. There's another example. And we're seeing that right now. In fact, from what I recall, and this is me talking, we are in the second week of April. Where I grew up, if I'm not mistaken, a lot of farmers were getting ready to plant their crops about this time of year. And it's snowing in a lot of places in the Corn Belt. And the weather is very erratic right now. So you're already seeing a disruption in the planting process because of erratic bad weather. Back to the bad weather. All that is needed is one unseasonal late snowfall or hailstorm to ruin crops for a season. These anomalies, including earthquakes and volcanoes see below, can be expected to increase generally along the usual risk zones for natural disasters. As a generalization, it can be said that for any given region, expect more of the same, plus in the long run, overall cooling and droughts. For the current trend of decline into solar minimum, since Earth's magnetic field is also weakening, the jury is still out over temperature progression and temperature change. During solar minimum, not only are there less sunspots, but there are also concentrated at the solar equator, whereas in... Wait a minute, let me read that again. During solar minimum, not only are there less sunspots, but these are also concentrated at the solar equator, whereas in solar maximum, they also appear in the range of 30 to 50 degree latitudes. Okay, I get that. That's true. What that means is during solar minimum, if there are any sunspots, they're mainly right at the equator, at the center of the sun. During solar maximum, sunspots drift above and below the equator and can become quite large. I've seen them many times during solar maximum. Big, bulky sunspots, and they are well above and well below the equator of the sun. Summary of the feedback loop climate downturn in grand solar minimum. 1. Weak solar magnetic field, weak solar wind. More cosmic ray influx from space. Ionization of atmospheric molecules, cloud nucleation. More cloud formation and erratic precipitation, long-term cooling. More clouds reflect solar radiation. More snow and ice reflect solar radiation. More long-term cooling. A grand solar minimum, as a succession of several very low solar cycles, occurs approximately every 200 years. The last notable one was the Dalton minimum in 1790 through 1820, which was followed by the end of the Little Ice Age, the Second Industrial Revolution, population expansion, and the beginning of the modern global warming trend, which began in 1850 and lasted until 2000. Flooding and droughts. In grand solar minimum, cosmic rays trigger larger flash floods, hailstorms, and, due to jet stream disturbance and mixing up atmospheric layers, local long-duration precipitation events. At the same time, as the increased local flooding events occur, more cloud cover and less sea surface water heating means less evaporation of seawater, specific humidity is reduced, overall rainfall amounts are reduced. Despite regional precipitation records and flooding, in general, water tends to remain in the cloud cover for longer durations. When clouds are rained out, this happens more violently. That's why we're seeing, like right now, we're seeing in places sometimes a year's worth of rain in 2 days. We've seen that many times over the last few months. And again, this is me talking. We've seen 6 months worth of rain in 12 hours. We've seen it in places. So this is already occurring. In general, water tends to remain in the cloud cover for longer durations. When clouds are rained out, this happens more violently, whereas the regular transport into the continents is diminished. As a result, in many areas, droughts are historically more prevalent during grand solar minima. This can be marketed as the result of global warming, implying man-made global warming. Of course, even though there has been no global warming since 2000. So due to the shifting jet streams and changing wind patterns, singular heat waves and more wildfires are expected. During the coldest period of the Maunder minimum, Alaska and the North Atlantic were even warmer than normal. Higher solar activity correlates very well with high specific humidity in the atmosphere. So, in the solar maximum, less cosmic rays means less clouds, more sunshine, but more water vapor in the atmosphere. Water vapor itself, gas, not condensed droplets, is a greenhouse gas, 10 times more effective than CO2. Thus, another feedback mechanism towards warming and stable weather is generated during solar maximum. In addition to the general higher humidity, fair weather means more difference between day and night temperature, also amounting to more dew formation. What this means for agriculture and civilization itself. In a minimum, lower specific humidity at the same temperature means lower relative humidity, which means less dew formation to nourish grass, plants. Most of these plants can sustain themselves from dew during extended rain-free periods on dry topsoil, whereas most of the more complex cultural plants require more ground moisture from regular rainfall or irrigation. Increased winds further accelerate soil drying. Dew forms on leaf surfaces with the aid of microscopic particles on the leaves, which serve as condensation nuclei. At night, when temperatures are low and thus relative humidity is high, that's how grass can be wet in the morning when everything else is dry. The condensed water droplets are then absorbed in the leaves or roots. Not only is animal husbandry based on grass growth, but cereals, wheat, rye, etc. are grass plants that can live on dew for extended periods of time. Thus, the related food production can be devastated by lower humidity alone. In grand solar minimum, local droughts and crop failure may be caused not only by less rain and more winds, but simply by lower specific humidity. This means this may not even show up on climate records, temperature and precipitation. Droughts in frigid climates lead to more sublimation of snow that is replenished by snowfall, evaporation of ice. Thus, glaciers may disappear from the top down in continuous sub-zero temperatures. This can be marketed as melting due to warming, for instance, on the peak of Kilimanjaro. UV radiation. Crop damage, local heating, wildfires, and biological damage can further be exaggerated by an increase in UV radiation by these mechanisms. There is a direct correlation of cosmic rays and ozone depletion. Ozone depletion, as at solar minimum, means more harmful UVB and C on Earth's surface. The ongoing reduction of the geomagnetic field strength lets in more cosmic rays and UV radiation. And I'm going to stop there. It goes on to talk about earthquakes and volcanoes. It goes on to talk about ocean warming, historical discussions, social and economic developments, solar maxima, astronomical trends, weakening Earth's magnetic field, the local bubble, the ongoing increase in cosmic rays and the next grand solar minimum, temperature predictions, and then that's about it. But I wanted to take you at least to the part where it talks about, in the article here, and it's a well-written article, talks about UV. Does it kind of make sense now? We're in a solar minimum. The magnetic field of Earth is the first line of defense against ultraviolet radiation. If it's not boxing with the sun, so to speak, the sun is in a high state of flux, it's in solar maximum. So the sun is juiced and it's got the Earth's magnetic field juiced. So it's not being lazy, it's blocking out cosmic rays from space, it's working better. During times of solar minimum, the magnetic field gets kind of lazy. Yeah, it's weakening. But to me, the reason it's weakening is because of the sun. The sun's getting quiet. So the shields basically have less to do because it's not, boxing every day with the sun like it normally is, which affects the UV. And just like he says here, at solar minimum, more harmful UVB and UVC on Earth's surface. So it's not unheard of, guys. It has happened before. The only problem is no UVC is good. But the bottom line is this. We don't know that much about what it would do at Earth's surface because it's never gotten through the ozone on a regular basis. UVB and UVC, if you just take a look around, and you're seeing things that look severely scorched, extremely dehydrated, more intense sunlight. And that tells you that the UV, or at least it tells me, that the UV is exceptionally high on those days, and it's very consistent. This year, the UV began an uptick in the spring, actually in the winter, and it stayed that way, and it's continuing to increase. But we'll get through it. It's going to be okay. I mean, it's not the first time this has happened, and it won't be the last. But just be wise during these times of change. If you're outside, like I've said a couple of hundred times, especially during the day, you know. I mean, it's even stated here in this article. We've showed you other articles at the website. UVC confirmed at ground level. Why? Did the same thing back during the solar minimum around 2007. We're seeing it again. Okay? Protect yourself. That's all. Just protect yourself. There's no reason to panic. None whatsoever. We don't want UVC to get way too high, or UVB for that matter. That's why we measure it every day. But during the hours of 10 a.m. and 4 p.m., use an umbrella, wear long sleeves if you can absolutely stand it, wear a hat and sunglasses, stay inside if you can. If you don't have to go out and do your shopping of an evening after the sun set. And we will get through this. It's gonna be okay. I'm telling you. Yeah, it's not cool to see UVC measured at the ground level because the ozone normally contains all of it in the upper levels of the atmosphere. But during times like this, when there are changes underway and all of these different components that make up the atmosphere are changing, then naturally things are going to change. So there is going to be an increase in the UV at ground level, but we will get through it. And this is a well-written article. I'll post it in the description box below if you're interested. I know this has been a long video, but I wanted to at least read up to the UV part. And there is another entire half of this article yet to go. It's a well-written article, and it's well-researched. But that's more than likely, guys, why the UV is getting higher. Okay? The sun's getting quiet. That means the magnetic shields of Earth are getting quiet. So the UV is going to increase. So it's going to affect weather. It's going to affect ocean currents. You know, the temperature, I don't think is going to change really that much. But you're going to see very unusual weather patterns. And quite possibly, you know, crop failures. Stay away from the UVC between the hours of 10 a.m. and 4 p.m. Like I said, just protect yourself. Stay inside if you can. And we'll be fine. Great article. You can find it in the description box below. Thanks for watching, guys. Have a super day and be safe out there.